after we have seen this wrapper design P15 or the IEEE 1500 standard and all that. So, the next step is to look into the system on chip and network on chip test architectures. So, system on chip is a design style in which we fabricate the entire system on a particular chip on a single silicon wafer, and in this network on chip what is done is that this communication problem that we get in today's IC. So, they are getting addressed by introducing some sort of on chip network to which these individual functional modules can be connected, and naturally testing issues they become more important, more severe in both the cases. So, system on chip and network on chip. So, in this part of the lecture, so we will be looking into those issues. So, what we will do is that we will introduce these basic and advanced architectures for system on chip testing and network on chip testing, and try to focus on this network or this on chip networks, testing of on chip network, and then some of the design practices followed. So, SOC testing is a composite test comprised of individual tests for each core, user defined logic and interconnect tests. So, what is there in an SOC is that in a single chip we have fabricated all these components. So, the individual cores are there, then we have got these interconnects between them, and also we have got some extra glue logic made put here and there to make the system complete. So, this testing process, it must test this individual cores, it must test this interconnect and also this user defined logic. So, all of them need to be tested and the SOC testing. So, to avoid this cumbersome format translation for IP cores, SOC and code development working groups such as Virtual Socket Interface Alliance have been formed to propose standards. So, what is happening is that, as we have already discussed, this SOC design, it is based on cores from IP vendors. So, IP vendors, when they are describing their description, so they are doing it in some format. As a system integrator, so the system or the designer, they take those designs and try to put them into their designs. Now they are naturally, if it is coming from two different group of bodies, then there is an interfacing standard problem. So, there is a Virtual Socket Interface Alliance that has been created, which is trying to address this issue, and they are trying to come up with different standards for this purpose. We have seen this IEEE 1500 that is that has been announced to facilitate this SOC testing. So, IEEE 1500 it specifies interface standards which allows code to fit quickly into the virtual sockets on SOC. So, if a core is supporting IEEE 1500, then it can be incorporated very easily into an SOC design paradigm, and that testing for testing purpose, this serial interface and parallel interface available for 1500, they can be exploited by the test engineer to design the proper test mechanism. So, core vendors, they provide cores with an uniform set of interface features, and system SOC integration is simplified by plugging cores into the standardized sockets. So, we have the designer might have designed these sockets previously, because what are the types of how to send different commands, what are the interfacing signals and all that. So, they are known once the standard has been fixed. So, based on that, they can tell like what are the requirements, and then the core vendor simultaneously they come up when they do their design in 1500 compatible format. So, they also know what are the commands that we need to support and what are the interfacing signals that should be there. So, that way the whole process becomes a bit simple. So, this is most of the time it can be a plug and play type of operation. So, core users generally cannot access core netlists and insert design for testability circuits. So, this is the major problem, because for say if we want to enhance the controllability and observability of a design, so we have to work at the netlist level. So, we have to know the at least at the logic gate level what are the components, and then if we by some fault simulation or something like that, we may know that okay, this part of the code is difficult to test. So, we put an observable point there, or we make that part controllable by putting some external input there. So, these may be tried out, but you see what is happening is that in this IP core based design, so we do the system integrator does not know the detail of the core. So, that is available with the core vendor, which is never told to the system integrator, because that is an the intellectual right is protected there. So, the core the users of the code, that is the system integrator, they do not have access to netlist, and they cannot insert design for testability circuits into it. So, core users rely on test patterns supplied by the core vendor. So, core vendor's responsibility becomes 2 point. One is to provide the layout level description of the system, and the second thing is to provide the test vectors or the test patterns that can be used for testing the operation of the code. Now, the problem that we have is that core vendor, they do not know in which platform this is going to be put. As a result, they try to make it as exhaustive as possible, and this system integrator also do not know the netlist. So, they cannot try out some sort of patterns to be more important or less important. So, like that. So, care must be taken to make sure that undesirable test patterns and clock skews are not introduced into the test streams. So, this is very important, as we have seen that the x values are to be stopped, unknown sources, and the clock skew are to be stopped when we are doing this testing. So, particularly that will affect your this compaction, the compression mechanism, compaction mechanism and all that. So, they are to be stopped. Okay. So, how, whether this has been taken care of by the core vendor or not, because as a design as an integrator one cannot take care of this because the details are not known. So, as from the core vendor's point of view, so this has to be done. Codes are often embedded in several layers of user defined or other code based logic and are not always directly accessible from chip input outputs. So, this is another problem with core based design, because the system input outputs are not directly feeding each and every core in the system. Now, in a normal circuit, we are handling the situation by doing some sort of justification through the logic, to the logic circuit or to the netlist. But in case of core based design, since the codes are coming from different vendors and they are the details are not known, so it is not possible to do a justification sort of thing, so that we can take care of this test pattern flow through to a particular code. So, they are not always directly accessible. So, test data at IOs of an embedded core might need to be translated into a format for application to the core. So, this is another issue. So, so maybe sometimes we need to do some format conversions. Maybe the test pattern has been stored in the ATE in some format, and then when it is applied to the circuit, applied to the core, so it needs some conversion. It is particularly true when we have got this test compression into picture. So, this test pattern that is stored in the ATE is in some encoded form, and in the encoded form the test data is transported to the transported somehow to the core, and then at that core we need to do something so that we get back the original test vector. So, it is like this. If this is say the system chip that we have, and this is the code that we are going to test. So, in the ATE, we have in the ATE memory, so we have stored the pattern, the test pattern for this particular code. Maybe in this region we have got those patterns, but as we know that they are not stored, often they are not stored directly as patterns, but they are stored in some coded form. And now this coded pattern somehow transferred to the input to the code, but this cannot be applied directly because they are. So, I need a translation from this coded form to the back to the original form. So, I need some sort of circuitry which is acting as a decoder, to get back the original pattern from this encoded bits that have been transferred. Now, this decoder becomes a glue logic. So, this decoder is part is designed by the system integrator, and that is possible because integrator knows like what are the patterns and then what is the encoding policy followed in that particular design by the group. So, that way they can design this decoder part, and this decoder part becomes a glue logic for the entire system. So, in the as the testing process is concerned, this decoder also has to be tested. So, it is not that we can take this decoder as correct, that may also develop some fault. So, that glue logic testing also becomes an important part. So, this typically shows what is happening in a testing of an embedded code based SOC system. So, we have got mainly 3 structural elements are required: test pattern source and sink, test access mechanism, and core test wrapper. So, this is a typical SOC that has got a number of components or number of modules like UART, ROM, SRAM, CPU, timer, DRAM, UDL, etc. Now, you see that suppose this is the circuit that we are going to test. Okay. So, that is marked as core under test and CUT. Now, as we know that every core is wrapped into a 1500 wrapper. So, this is the wrapper design that we have. So, we will see how this wrapper design can be done. So, this wrapper has been designed, and from the source the test patterns they had to be transported to this core under test, and the responses are to be collected and sent to the sink. So, that is the responses they are collected at the sink. So, this is what is required. Now, how this TAM can be designed, so that is an issue. So, somebody may say okay, I know the pattern, so I will make the pattern this modules such that this CPU, so it will be transferring the patterns through it and it will be applying to this card. But that is a very I should say very high expectation from the operation of this particular core, and without knowing the details of this, so it is very difficult. So, very often what is done is that we make some alternative arrangement, maybe in terms of some separate test lines through which these patterns are applied from source to this core under test and from the core under test to sink. So, these are the 3 things that we need: the wrapper design, the TAM design, and the test source and sink. So, these are the 3 parts that are needed for testing individual cores in a SOC. So, once test data transport mechanism and test translation mechanism are determined, major challenge for system integrator is test scheduling. So, we have decided like what should be my TAM or our TAM architecture, what should be the translation mechanism. So, test wrapper. So, what happens is that maybe my core has got a number of scan chains, and this maybe my core has got say 5 scan chains, and the number of pins that are dedicated for testing this particular core is say 3. That means this 5 scan chains, so they need to be converted into some form, so that ultimately these 3 inputs are feeding this 5 scan chains. So, this type of modifications are needed in the wrapper design phase. So, apart from that wrapper cells that we have seen previously while discussing on boundary scan part of the course. So, apart from ensuring how these parallel bits can be transferred, etc., some more things are to be done, because individual codes may have different number of scan chains, different number of inputs and outputs, and we may not be able to dedicate so many pins for feeding all those inputs parallelly. So, we need to convert some of them to serial one. So, that is basically a part of the test wrapper design problem. Apart from taking the other part, other things like say this wrapper control part, this bypass register, the buffer register, boundary scan register and all that. So, apart from those things, so this scan chain management becomes an important issue. And assuming that all these have been done, so we have decided on the test access mechanism, we have decided on this translation mechanism, the test wrapper design. So, main challenge becomes test scheduling. The test the system integrator has to perform scheduling of test for these different components. So, that becomes an important issue. So, test scheduling must consider several conflicting factors like the test minimization, SOC test time minimization. So, as we have already said that since this SOC has got a SOC may have a large number of cores, and each core vendor might have provided large number of test patterns. Now, all of them are to be applied, so that increases the test session length. So, we want to minimize this test time. So, for minimizing this test time, one possibility is we want to parallelize number of tests, but if we want to parallelize number of tests for the number of cores to be tested, then I need to feed all those cores with the test pattern. So, that in turn requires large number of pins to be there, large number of ATE channels to be there to transfer the test patterns. So, that way this is one conflicting requirement, that is the test time has to be minimized, whereas the second important conflict that we have, there are resource conflicts. So, if we want to minimize time, so resource conflict may not allow us, like sharing of TAMs, like the same test access mechanism may be utilized for controlling a number of cores. So, they are all of them are getting input from the same TAM. So, I cannot transport test data of two cores, two or more cores simultaneously on the same TAM. So, it has to be exclusive, or it may so happen that some of the cores are beasted, but they do not have the beast engine with them. So, in my whole SOC there may be a number of beast engines who can provide this beast patterns to the system. It is particularly true for these memories, like if many a system that are designed today, they have got large number of memories in them, and these memories they have got this type of beasted design. So, they use some beast for getting the test patterns. Now, if there are a number of memory modules, so putting beast for all of them separately may be costly. So, only for a few beasts are kept, and then beasts are allocated to different memories at different points of time. So, the test scheduler will find out which beast to be allocated to which core or which memory for testing at some point of time, and that way these beast engines are to be utilized. So, there may be conflict in beast engines. So, even if I want that a multiple number of memory tests should go parallelly, due to this restriction on the number of beast engines, so that is not possible. Precedence constraints among tests. So, it may so happen that one module it generates some inputs that are relevant for testing another core. So, one core generates some module, some output which is relevant for testing another core. So, in this type of situation, until unless the first one is tested, the next one cannot be tested. So, there may be some precedence constraint among the tests. And finally, the power constraints. So, most of these systems that we are designing today, VLSI designs, so they are going to be low power. So, low power means there will be a power limit for the chip, and then the chip should not consume more than that power. Now, the designers, they have got many facilities, because what they can do is that they can turn off some part of the chip, they can segment, they can partition the chip into different portions in terms of the number of modules that need to be on simultaneously. So, that way the power budget can be decided. But for the test engineer, what is happening is that now in an effort to do this test fast, we may like to turn on different modules simultaneously, and as soon as we do that, it may so happen that two modules which are normally switched on in an exclusive fashion, in a mutually exclusive fashion, they get turned on simultaneously. So, if they are consume lot of power, then this power consumption during testing will go up. So, that is that these are conflicting, like if I want to minimize this SOC testing time, maybe I will violate some power constraint. If I want to be within the power limit, so I just schedule, let us say, one core at a time, then the test time requirement will be very large. If I want to test a number of memory chips memory cores simultaneously, then this beast engine, it becomes a constraint. So, that is, and some certain test I cannot do in an arbitrary order due to this precedence constraint. So, these are the problems that are there in the testing process of this SOC. And analog and mixed signal code testing, it must be dealt with. So, no system which interacts with the environment is purely digital. So, there must be some analog part in it and some mixed signal part will be there. So, analog and mixed signal they are to be taken care of, and testing this analog and mixed signal course is challenging because their failure mechanisms and test requirements are less known than digital ones. So, analog test is not yet very well developed. So, many of the cases, so they this analog circuit they use similar type of procedure for testing digital circuits, but it is not yet well developed. Normally some sort of this current testing, current measurements are taken to check the correctness and all that, but that is not a very not yet very standard one. So, this analog and mixed signal testing becomes an important issue, but when we are talking about SOC testing, so we cannot ignore this analog mixed signal testing. So, this SOC testing, so we will go like this. So, we will motivation for modular testing of SOC, then we will look into this wrapper design, IEEE 1500 standard and optimization, test access mechanism design, test scheduling. Okay. So, these are the various problems. Okay. So, this wrapper design is an important problem. Then apart from this 1500 standard that we have discussed, so we need to do some sort of optimization. So, the optimization part we will see. For a particular code, there may be different wrappers that we can come up with, and that may decide this testing time of that code. Then this test access mechanism design, like how do we, so we have seen some test access mechanisms, but what are the alternatives. Then once we have decided on this wrapper and test access mechanism, what sort of scheduling policy can we follow. Then there are some codes, they have got some special feature, like they can have some port scalability. So, port can be made to operate at different frequencies, it can support multiple data rates, like there is something called virtual TAM, then the ATE can provide data at higher rate. So, that way it can be taken care of. So, there are many things to be taken care of in the SOC testing. To start with, so these system chips, so they are having about 50 million transistors in a 1 centimeter by 1 centimeter area. So, just for a comparison, the viruses, the size is 300 nanometer, so even much smaller than this, and this Intel Itanium that came up in 2006 is 1.7 billion transistors. So, its size is naturally it has got a very large number of devices. So, the possibility of failure is very large, and this actually shows that how this with the advancement in technology, how these transistors are going. So, this is 2001, where the this gate length was about 70 nanometer, then 2005 it came down to 30 nanometer, then 2007 20 nanometer, and 2009 15 nanometer. So, that way this gate length is reducing. So, that makes it more susceptible to many faults. So, Intel has crafted transistor with 20 nanometer gate length. So, that came up with 2001 actually. So, this way we have got different, so that shows the speed at which this design community they are progressing. So, that these devices are becoming smaller and smaller, and that way we can put many devices into a single chip. Okay. But that way the possibility of failure or possibility of defect, so that increases. So, possibility of faults also increases. So, why is it so much important to do this type of detailed testing? So, there is an Xbox 360 technical problem. So, it says the red ring of death problem. So, there it's on an Xbox there are 3 light indicators, 3 red lights, Xbox 360 indicator representing general hardware failure. So, this is available as an Wikipedia article. Then this can be subject to a number of possible technical problems. Since this console was released 2005, the console gained a reputation in the press in articles portraying poor reliability and relatively high failure rates. So, since actually all cases could not be covered in the design of Xbox, all the failures could not be covered. So, it was kept that if something hardware failure is detected, so it will glow it will have a red ring, 3 red lights will be there, and then the system has to be reset. So, that is an error, and it started occurring very frequently. And ultimately on 5th July 2007, Peter Moore published an open letter recognizing the problem and announcing 3 years warranty expansion for every Xbox console that experiences the general hardware failure indicated by the 3 flashing red lights on the console. So, this is actually a great loss, because they are extending the warranty because of this hardware failure. So, need to extend the warranty. So, that becomes a great loss. So, that indicates that why is it so important to do testing. July 5, 2007, Xbox issues to cost Microsoft $1 billion, more than that. So, that is an unacceptable number of repair leads to company extending warranty. So, the warranty has to be increased, and then that caused so much of loss. And Matt Rossoff, an analyst at the independent research group Directions on Microsoft, estimates that Microsoft's entertainment and device division has lost more than $6 billion since 2002 due to this Xbox. So, that actually tells the system may become complex, but we cannot avoid this testing. So, testing has to be done, and it has to be done very exhaustively.